Cloudy climate change. How clouds affect Earth's temperature. Earth's average surface temperature has warmed by 0.8 Celsius since 1750. When carbon dioxide concentrations in the atmosphere have doubled, which is expected before the end of the 21st century, researchers project global temperatures will have risen by 1.5 to 4.5 degrees Celsius. If the increase is near the low end, 1.5 Celsius, then we're already halfway there, and we should be more able to adapt, with some regions becoming drier and less productive, but others becoming warmer, wetter and more productive. On the other hand, a rise of 4.5 degrees Celsius would be similar in magnitude to the warming that's occurred since the last glacial maximum 22,000 years ago, when most of North America was under an ice sheet 2 kilometers thick. So that would represent a dramatic change of climate. So it's vitally important for scientists to predict the change in temperature with as much precision as possible so that society can plan for the future. The present range of uncertainty is simply too large to be confident of how best to respond to climate change. But this estimate of 1.5 to 4.5 Celsius for a doubling of carbon dioxide hasn't changed in 35 years. Why haven't we been able to narrow it down? The answer is that we don't yet understand aerosols and clouds well enough. But a new experiment at CERN is tackling the problem. In order to predict how the temperature will change, scientists need to know something called Earth's climate sensitivity, the temperature change in response to a radiative forcing. A radiative forcing is a temporary imbalance between the energy received from the sun and the energy radiated back out to space, like the imbalance caused by an increase of greenhouse gases. To correct the imbalance, Earth warms up or cools down. We can determine Earth climate sensitivity from the experiment that we've already performed in the industrial age since 1750, and then use this number to determine how much more it will warm for various projected radiative forcings in the 21st century. To do this, we need to know two things. First, the global temperature rise since 1750, and second, the radiative forcing of the present-day climate relative to the pre-industrial climate. For the radiative forcings, we know that human activities have increased greenhouse gases in the atmosphere, which have warmed the planet. But our activities have, at the same time, increased the amount of aerosol particles and clouds, which have cooled the planet. Pre-industrial greenhouse gas concentrations are well measured from bubbles trapped in ice cores obtained in Greenland and Antarctica, so the greenhouse gas forcings are precisely known. But we have no way of directly measuring how cloudy it was in 1750, and that's the main source of uncertainty in Earth's climate sensitivity. To understand pre-industrial cloudiness, we must use computer models that reliably simulate the processes responsible for forming aerosols and clouds. Now, to most people, aerosols are the thing that make your hair stick, but that's only one type of aerosol. Atmospheric aerosols are tiny liquid or solid particles suspended in the air. They are either primary, from dust, sea spray salt, or burning biomass, or secondary, formed by gas-to-particle conversion in the atmosphere, also known as particle nucleation. Aerosols are everywhere in the atmosphere, and they can block out the sun in polluted urban environments or bathe distant mountains in a blue haze. More importantly, a cloud droplet cannot form without an aerosol particle seed. So without aerosol particles, there'd be no clouds. And without clouds, there'd be no fresh water. The climate would be much hotter, and there would be no life. So we owe our existence to aerosol particles. However, despite their importance, how aerosol particles form in the atmosphere and their effect on clouds are poorly understood. Even the vapors responsible for aerosol particle formation are not well established, because they're present in only minute amounts, near 1 molecule per million molecules of air. This lack of understanding is the main reason for the large uncertainty in climate sensitivity and the corresponding wide range of future climate projections. However, an experiment underway at CERN, named, perhaps unsurprisingly, CLOUD, has managed to build a steel vessel that's large enough and has low enough contamination that aerosol formation can, for the first time, be measured under tightly controlled atmospheric conditions in the laboratory. In its first 5 years of operation, Cloud has identified the vapours responsible for aerosol particle formation in the atmosphere, which include sulfuric acid, ammonia, amines, and biogenic vapours from trees. Using an ionising particle beam from the CERN proton synchrotron, Cloud is also investigating if galactic cosmic rays enhance the formation of aerosols and clouds. This has been suggested as a possible unaccounted natural climate-forcing agent, since the flux of cosmic rays raining down on the atmosphere varies with solar activity. So Cloud is addressing two big questions. Firstly, how cloudy was the pre-industrial climate, and hence, how much have clouds changed due to human activities? That knowledge will help sharpen climate projections in the 21st century. And secondly, could the puzzling observations of solar climate variability in the pre-industrial climate be explained by an influence of galactic cosmic rays on clouds? Ambitious but realistic goals when your head's in the clouds.